All right, so like I said, we're jumping into chapter 4, so this is 4.1. We're going to talk about radians and degrees. And the first part, we're going to go over some terminology, some of the vocabulary that we're going to use when we're talking about trigonometry, and then we're going to talk about how we're going to use these particular tools that we're working on. So trigonometry, what we're interested in is angles. So let's talk about what an angle is, what we mean by an angle. So if I draw my set of axes here, and this is x, and this is y, an angle just means we have two rays that have the same starting point. So I'm going to draw my angle here. I'll draw the angle in red, and I'll do it this way. So there's my angle, like so. And our angle is just the amount of rotation to get from one side to the other side of the angle. So usually we call this side of the angle, it's along the x-axis. We start on the x-axis just to make it easier. This is our initial side. We call this side of the angle the terminal side. And our angle is how much we have to rotate to go from the initial side to the terminal side. And we usually label angles theta. I don't know why they chose theta for angles, but that's just kind of math tradition to name angles theta. If we're talking about a positive angle from our initial side, we're rotating counterclockwise. So that would be positive. If we're rotating clockwise, we would have a negative angle. So positive angle means we're rotating counterclockwise. Negative angle means we're rotating clockwise. The point here where the two rays meet is the vertex. And we call an angle's in standard position if our vertex is at the origin and our initial side is on the x-axis. So this angle would be in standard position. So two angles, the other piece of vocabulary that we need, two angles in standard position where the terminal sides are in the same place are called coterminal. So it just means that the terminal side is in the same place. And the reason you would think that if an angle was coterminal, it would just be the same angle. But we can get to this terminal side by rotating this amount, or we could rotate all the way around the circle to that amount, or we could rotate around this way and get to that same terminal side. So we can rotate around more than once and get to the same place, and we can rotate the other direction. So a lot of times your questions will ask you, name two coterminal angles for a particular angle. So, and it'll ask you, give a positive and a negative coterminal angle. So coterminal, again, just means the terminal side is in the same place. So we're in standard position. And they share the terminal side. So to find coterminal angles, to find a positive coterminal angle, we're going to subtract pi or 360 degrees, and a negative angle we're going to add, or sorry, we're going to subtract from 360. And to find a negative coterminal angle, we're going to add. I'm going to change this, not subtract from 360, but subtract 360. So we can find our coterminal angles just by adding or subtracting 360 degrees. That will give us different coterminal angles for the angle that we're interested in. And when we talk about the quadrant that the angle lies in, a lot of times we're interested in the quadrant. The quadrant that the angle lies in is asking what quadrant is the terminal side in. So we just want to know what quadrant the terminal side of our angle is. So a question might ask you what quadrant is an angle of 240 degrees, and we're trying to figure out what quadrant the terminal side is in if the angle is in standard position. So any questions on this terminology? Yes. So we have an angle, say our angle is 20 degrees. We want a coterminal angle, a positive coterminal angle. We would subtract 360 degrees from our angle. Yes.
And like if it was a homework problem, would it just say find the coterminal positive coterminal?
Some of the homework problems will say find a positive and negative coterminal angle for this angle.
Okay.
All right. Next thing we need to talk about is radian measure. So this is where we've used degrees almost pretty much since we've been in elementary school. We have an idea of what a degree is, what 360 degrees is, what 90 degrees is. So we're relatively familiar with the idea of degrees. Radians, when we're doing trigonometry, radians is going to be a more useful measure of angle. We're often going to use radians instead of degrees. So let's talk about radian measure. So radian measure has to do with the arc length and the radius of the arc length that the angles that the angle moves through and the radius of the circle. If we think of the side of the circle, the side of our angle rotating around and making a circle, radian measure has to do with the arc length of the circle and the radius of the circle. So let me draw another picture and we'll talk about radian measure. So we need our axes again. And if we draw our angle in here in standard position, so here's the initial side, we come up here to the terminal side, and we're rotating from this point around to this point. And this, we're thinking of this making a circle. So this ray rotates around and makes a circle. So the length of this ray here is the radius of the circle. So that's the radius of the circle. I'm going to label that R. R. This is our angle. And we usually use the letter S for arc length. And we're going to say on this particular circle that the arc length we've rotated through just enough angle so that the arc length equals the radius. We've rotated through an angle of 1 radian when the arc length of the piece of the circle that we've made equals the radius. So 1 radian is the angle where the arc length equals the radius. That's how we define 1 radian. We define 1 radian as the angle that we need to rotate through so that the arc length equals the radius. So what we say, the way we're going to calculate this, is radian measure for a piece of a circle. If we're thinking about rotating around a piece of a circle, the radian measure is, we write as S over R, or the arc length divided by the radius. That's how we tell how many radians. Radians is just another way of measuring an angle. That's how we tell how many radians we've rotated our angle through, is by dividing the arc length that's made by the piece of the circle that we've rotated through by the radius. There's a little easier way to work with it, because if we go around the circle 1 full time, what's the arc length? If we rotate around the circle the entire time, the arc length is what part of the circle? So if I have an angle here and I rotate all the way around from here, rotate all the way around the circle, what part of the circle is the arc length? The circumference. So if I rotate all the way around the circle, the arc length is the circumference of the circle. So the arc length equals the circumference. And how do we find the circumference of a circle? What's the formula for circumference? 2 pi r. Perfect. So the circumference, and we're saying we're looking at the arc, we're thinking of the circumference as the arc length as we're rotating our angle around. The circumference equals the arc length equals 2 pi r. So S over r, this tells us that S over r, which is how we defined our radian measure, is, if I divide both sides of this equation by r, I get 2 pi. So this tells us that when we rotate around a circle, we've rotated through an angle of 2 pi radians. So there are 2 pi radians. So when we rotate around the circle one full time, our ray, our terminal side of our ray, has rotated through a radian angle measure of 2 pi radians. So we have 2 pi radians in one full circle. Now let's look at the units of radian measure. What are the units of arc length? Length, time, volume, mass. What would be our units of arc length? Length. I call it arc length, right? So our unit of arc length is length. That's our unit. So it'd be inches, meters, centimeters. So our unit of arc length is a unit of length. What units do does the radius have? Mass, volume, time, length. Radius is also a unit of length. So arc length and radius have the same units. So if I divide length by length, the units cancel. So we say that radians don't have any units. So radians don't have units. So that's one little interesting thing about radians. So it makes them nice to calculate because we don't have to keep track of the units. With degrees, the unit of degree is degree. So that we have a unit when we measure in degrees. When we measure in radians, we don't have to worry about units. Radians don't have units. So let's think about if we know that we have 2 pi radians in a full circle, let's think about some common angles. If we have 2 pi radians in a full circle, how many radians would be in a half a circle? If we go around halfway. Pi. So half a circle is pi radians. 90 degrees? 1/2 pi, we usually say pi over 2 or pi halves. I usually say pi over 2. So 90 degrees is pi over 2 radians. 45 degrees would be pi over 4. And 60 degrees is a little trickier. Pi over, what did you say? Pi over 3. 60 degrees is pi over 3. 30 degrees is pi over 6. And we'll talk about those more later. But we can think about how far we've gone around the circle to figure out how many radians are in our common measures. So halfway around the circle is pi radians. A quarter of the way is pi over 2. 45 degrees is half of pi over 2 or pi over 4. So those are some of our common angle measures. So let's write those down. So the common angles. 180 degrees we said was pi radians. 90 degrees is pi over 2. 45 degrees is pi over 4 radians. 60 degrees we said was pi over 3. 30 degrees was pi over 6. And we'll work with these common angles more when we talk about the unit circle. So before we go on, any questions about radians? Yes.
Yeah, I'm not quite sure how you did it, like the pi over 4 or whatever, all the different.
Okay. So we said that if we go around the circle one whole time, it's 2 pi radians.
Mm-hmm.
So if we go around half, we would divide 2 pi by 2. So 2 pi divided by 2 is just pi. So that's halfway around is pi. If we're going around a quarter of the way, we would divide 2 pi by 4 and get pi over 2. And if we go around 45 degrees, we're going around an eighth of the way, so we divide 2 pi by 8. So we're just dividing by what fraction of the total distance around we've gone to get these fractions. And we'll talk about, the next thing I want to talk about is how to convert from radians to degrees and back. So radians tell us our measure of angle. We have 1 radian when we've rotated enough that the arc length of the piece of the circle that we've made equals the radius of the circle. And that lets us say that 1 full circle is an angle, contains an angle of 2 pi radians. So let's talk about converting from angles to radians. Pretty easy. So talking about degree measure, if we have an angle of 1 degree, the way we've defined an angle angle measure is we say that 1 time around the circle is 360 degrees. So 1 degree is just 1/360th the way around the circle. So 1 full circle is 360 degrees. 1 degree equals 1/360th of a rotation around the circle. So since we know that there are 2 pi radians in the full circle, and we've said that there are 360 degrees in a full circle, we can say that a rotation of 360 degrees is equal to a rotation of 2 pi. And we said if we divide both sides by 2, we already said that 180 degrees equals pi radians. So 1 radian, and I'm going to write rad for radian. 1 radian is 180 degrees divided by pi. So this tells us how we can convert from radians to degrees and from degrees to radians. To convert degrees to radians, we're going to multiply by pi over 180. And this will give us our radians. radians to degrees. We're going to multiply by 180 over pi. So if we have degrees, we want to convert to radians, we multiply by pi over 180. If we have radians, we want to convert to degrees, we multiply by 180 over pi. So let's do a couple of examples of conversions. Any questions before we go on? So if we have, if we want to convert 120 degrees to radians, we just do 120 times pi over 180. And I get, if I reduce this fraction, I get 2 pi over 3. And usually with radians, you want to leave it as a fraction. You want to write 2 pi over 3. You don't want to write this as a decimal. You want to use an exact measure. And if we want to multiply, if we want to convert negative 315 degrees equals negative 315 times pi over 180, and that would give me negative 7 pi over 4. And to get these fractions, I'm just reducing these fractions. Yes? That was just we want to convert negative, our problem was to convert negative 315 degrees to radians. This is a separate example. 120 is 2 pi over 3. 315 degrees is negative 7 pi over 4. So this is example A, and this is example. They're two separate problems. And again, we don't write units for radians. Radians don't have any units. If we want to go the other way, we want to go to 5 pi over 6, 2 degrees. So we're going to multiply 5 pi over 6 times 180 over pi. Our pi's are going to cancel, and we just have to work with this fraction, and this turns into 150 degrees. Our pi's cancel, multiply 5 times 180, divide by 6, and I get 150 degrees. They don't always come out perfect. Just turned out that way in this example. And if we had 7 radians, so our radians don't always have to have a pi in them. We can have a measurement of 7 radians. So let's think about how big 7 radians would be. How many radians if we go around the circle one whole time? That's 2 pi radians. How many is that if we convert that to a decimal? 2 pi? Pi is 3.14. So 2 pi is a little more than 6, right? So 6.2-ish, right? So one rotation all the way around the circle is only 6 radians. So 7 radians is going to be more than one rotation around the circle. So that gives you an idea of how big 7 radians is. 7 radians is 7. We're just going to multiply by 180 over pi to convert to degrees. And we get 10 pi over 3, I'm sorry, we get 1260 over pi. 7 times 180 is 1260, divide by pi, and that is approximately equal to 401.07 degrees. So all the way around the circle is 360, so we've gone around 401. Seven radians is 401 degrees. Questions on conversions? Or we need to talk about a couple of other things about a couple of other terms that have to do with angles. Acute angles. Do you remember in degrees what an acute angle is? Less than 90, so between 0 and 90. So in radians, what would that be? Between 0 and pi over 2. So an acute angle is between 0 and 90, or 0 and pi over 2. Obtuse? Above 90, perfect. Above 90, below 180. So in radian measure, that would be above pi over 2, below pi. So obtuse angles are between pi over 2 and pi. Acute angles are between 0 and pi over 2. How about, do we remember what complementary angles are? Angles that add up to something, not 360, 90. 90. Did you say, what did you say, Colin? You said 90? All right, complementary angles, they add up to 90. So in degree measure, or I'm sorry, in radian measure, what are they going to add up to? Pi over 2. And for complementary angles, we are saying that we have two positive angles. So both of our angles need to be positive. And so now that we got complementary, I think we can get, what about supplementary? Supplementary angles add to 180. And in radian measure, add to pi. So some of your homework problems will ask you to find the complement and supplement of an angle. So if we have an angle, how are we going to find the complement? 90 minus, or in radians? Pi over 2 minus whatever your angle is. So to find the complementary angle, you subtract from pi over 2. To find the supplementary angle, you're going to subtract from pi. So when it asks you to find the complement and supplement, you're either subtracting from pi over 2 or you're subtracting from pi. All right. Questions on what we've done so far? A lot of this is review, but the radians might be a little bit new, and we're going to work with radians quite a bit this semester. So we're working on getting familiar with radians. All right. So I need to talk about a couple of applications, and then show you one other conversion, and then we're done. So applications. Now with Radian measure, we said that our angle theta is S over R, arc length over radius. So we can say, if we're working in radians, we can say that the arc length S is R times theta. So our arc length, we can figure out, if we know our radius and we know what angle we've rotated through, we can figure out what the arc length, how long that piece of the circle is that we rotated through. Now it's important to remember, this only works in radians. Only with radians. Does not work with degrees. So one example would be, we want to find the arc length that a central angle of, this is the way the problem might be given to you in your homework. So the arc length of a central angle of 120 degrees in a circle with radius 5 inches. So we're looking for this arc length. The problem might ask you, you have a scale in a grocery store, and the arm of the scale moves through 120 degrees, and the arm of the scale is 5 inches long. How far does the tip of the arm of the scale travel? That would be an example of a problem like this. So we're looking for that arc length. How far does that angle, the tip of that angle, travel as it rotates through 120 degrees? So for this one, what do we need to do first? We have to work in radians. So our first step is 120 degrees to radians. So we have to switch it to radians. So 120 degrees to convert times pi over 180, and I get, what does this come out to? 120, 2 over 3? 2 pi over 3 or 2/3 pi, either way is fine. So we have 2 pi over 3 radians. And our second step, we can find our arc length. S equals r theta. So our arc length our radius is 5 inches times 2 pi over 3. And I get 10 pi over 3 inches. If your problem asks you for the exact answer, you would leave this pi in here, 10 pi over 3. If it asks you for the approximate answer rounded to so many decimal points, you plug this into your calculator. So that would be approximately 10.47 inches, if we calculate that out. Yes. That's a 5. And I need to be more careful. I should write my S's curvier, because my 5's and S's kind of look the same. So there's S, and this is a 5. 5 from our radius. So questions on this kind of problem? Now we can also translate this arc length into velocity and angular velocity. So if we're talking about a wheel turning, a wheel turns through so many radians per second when it's turning, depending on its radius. The bigger wheel turns, the linear velocity, the outside of the wheel is turning faster than a smaller wheel if it's moving through the same number of radians per second. So we can work on problems that have to do with velocity and angular velocity if our angles are in radians. So let's look at an example of that. And the formulas that we're going to use for those types of problems, since S equals R theta, our arc length is equal to the radius times our angle. If we divide everything by time, by the time that we're measuring, I'm going to divide by t. Because distance equals rate times time, so we're talking about our velocity. Velocity is rate divided by time. Divide by time, so I get S divided by t equals r times theta divided by t. And we have some symbols for S over t and theta over t. So S over t is just our velocity. The arc length divided by time is just our velocity, or linear velocity. So we write that v equals r, and our radians per second, or radians per minute, we call omega. And what this is telling us is linear velocity equals radius times angular velocity. Omega is a measure of angular velocity. So omega is our symbol for angular velocity, radians per second. So this is in length per second. Omega is in radians per second, or radians per minute, or radians per hour, or something like that. So our linear velocity is radius times angular velocity. It's the same formula that we've just been using. We've turned it into a velocity instead of just a length problem. So an example of this type of problem that you might see is we have a car that's traveling at 65 miles an hour. And the tires have a radius of 15 inches. So we have 15-inch tires, and we want to know at what rate in revolutions per minute are the tires spinning? So we have a linear velocity, 65 miles per hour, and our revolutions per minute has to do with our angular velocity. So couple of things that we have to do here. We have 65 miles per hour, and our tires are 15 inches. So we need to get everything in the same units. So we need to get everything in the same units. So let's convert miles per hour into inches per minute. Our tires are in inches, and we want revolutions per minute. So we need to convert our units. So that's going to be my first step. So I'm going to do 65 miles per hour. Does anybody know how many inches are in a mile? 5280 feet. So we need to multiply that by what? 12. So if we multiply 5280 by 12, we should get 63,360. $63,360 inches per mile. And we need to convert our minutes. So we want inches per minute. So 1 hour is how many minutes? 1 hour per 60 minutes. So if I do this conversion, multiply 65 by 63360, divide by 60, I get 68640 inches per minute. So our linear velocity is 68640 inches per minute. So there's our linear velocity. And we want to find, the first step is we want to find the angular velocity. So let's find our angular velocity. So from this formula, V equals R omega. We can divide both sides by R. So omega equals V over R. We just found our linear velocity, 68640. So we have 68640 inches per minute, divided by our radius, which is 15 inches. And when we divide that out, we get that omega equals 4576 radians per minute. So that's our angular velocity. Is that what the problem asked us to figure out? No, it asked us to figure out revolutions per minute. So we need to do one more conversion. How do we go from radians per minute to revolutions per minute? How many radians per revolution? 2 pi. So we're going to convert to RPM, revolutions per minute. So we're going to multiply 4576, and I'm going to write rad per minute times 1 revolution per 2 pi radians. So I'm dividing by 2 pi. So our RPM, when I divide 4576 by 2 pi, I get about 728. Finally, 0.29 revolution per minute. Questions on that one? All right, there's one other conversion I need to show you. There's a couple of problems in your book, and it'll come up throughout the course of the semester, where we need to convert from degrees to hour, minute, second. So let me show you a little bit about degrees, hour, minute, second, and I'll show you how to do it on your calculator. So sometimes you'll see angles, and this is a little older way of notating angles, but sometimes you'll see it written that you'll see an angle written as, for example, 245 degrees, 10 minutes, 34 seconds. That's what this means. 1 minute is 1/60th of a degree. One second is 1/3600th of a degree. So if we wanted to convert this to decimal, we would have 245 degrees. We would have 10 minutes. So if we wanted to convert, we would say that 10 minutes times 1/60th equals 0.166. So 10 minutes is 1/60th of a degree, so 10 minutes is 0.166 degrees. 34 seconds is 34, we're going to do 34 times 1/3600th of a degree. And that gives me 0.0094. And then we would add those together. So we would have 245 degrees plus 0.166 degrees plus 0.0094 degrees. So that would equal 245.175 degrees. The question would say convert would give you the angle in this notation, 245 degrees, 10 minutes, 34 seconds, and then it would ask you to calculate something with it or do something with it, like find the arc length. Find the arc length of an angle of 245 degrees, 10 minutes, 34 seconds, if the radius is 7 inches. And we don't know how to work with degrees, minutes, seconds, unless we convert it to decimals. Or the question might just ask you convert this to degrees. So just it's asking you to be familiar with this notation and what it means. Let me show you how to do it in your calculator. It's going to be a little easier. So in your calculator, so we're going to do the same conversion. So I'm going to do 245, and then I'm going to go to this button that says angle. I'm going to do second, go to angle, and number 1 is degrees. So I'm going to hit, so that tells me it's 245 degrees. I had 10 minutes, so I'm going to do 10, and then I'm going to go back to angle. And this is my minute, so I'm going to go down to 2. So that's 10 minutes. And we had 34 seconds. 34. Our seconds are right here next to the memory in the plus button. So I'm going to do that one. 10 minutes, or 245 degrees, 10 minutes, 34 seconds. And I hit enter. And I get 245.176. Yeah, so I hit the alpha to get the little green seconds. Yes?
So that's 245.176.
Degrees. So this converts it from degrees, minutes, seconds to just degrees in decimal notation. 245.176. When I did it, I came up with 0.175, so I just had to do it how I rounded. And if I want to convert back, so if I have 245.176, I'm going to go to my angle button. So second, go to angle, and this number 4 converts it to degrees, minutes, seconds. I hit enter, and it converts it back. So that's how you're going to convert back and forth on your calculator. And there are a couple of problems that will ask you to convert. There are a couple of problems that will give you an angle in degrees, minutes, seconds, and ask you to work with it. Before you work with it, you need to convert it to decimal degrees. All right, are we all good?
Can you show how you got like the level?
Yes. So let me put in another angle. So let's say I have 345 degrees. So I'm going to do 345. This is the degrees. So I'll hit enter. And I have, say, 7 minutes. 7. I'm going to go to minutes. So this is that. Minutes are in the angle also. That's here. And then the seconds. Let's say I have 12 seconds. The seconds are here. So I did alpha and then the plus button. The 245 degrees, 7 minutes, 12 seconds, and then I can convert that to decimal, 245.12. Yes. Yeah, you go to angle, so second, you go to the angle, and then this number 4, the arrow 2 DMS means 2 degrees, minutes, seconds. Hit enter, it'll come up with this, and I hit enter again, and it converts it back. Okay? All right, I'm done talking. Homework. All right, there you go.